Welcome to Road and Pavement Design tutorial number 8. In this tutorial we are going to discuss the design of rigid pavements according to the Portland Cement Association method. As I said in tutorial number 6, design of flexible pavements according to Asphalt Institute method, the mechanistic empirical approaches of design follow this chart here, where you assume a trial design thickness based on some inputs like traffic, foundation, climate, material properties. This trial design results in some structural responses in the form of stresses, strains, and deflections, and these structural responses are linked empirically to the distress prediction models to obtain the distresses in the pavement due to the structural responses. In the PCA method, the two distresses that are taken into consideration are the fatigue and erosion. Finally, you have to check whether the distresses are within the allowable limits or not. If it meets the performance, then your trial design was right. If it doesn't meet the performance, then you have to increase the concrete slab thickness, then check again this cycle until you meet the performance criteria. Now let's talk about the origin of the PCA method. The PCA method for concrete pavement design is based on a combination of theoretical studies, results of finite element models, and experience gained from the performance of concrete pavements that carry traffic loads in order to create the design charts. PCA method is a mechanistic empirical method, so it is an iterative design process where you assume the thickness of concrete and check pavement performance in terms of two distresses, which are fatigue and erosion, and as I said in the previous slide. So, fatigue keeps pavement stresses due to repeated loads within the safe limits to prevent flexural failure. As you can see here, this failure happens due to fatigue, which happens due to repeated loads on the concrete slab. Erosion limits the effects of pavement deflections at edges, joints, and corners to prevent faulting and pumping. As you can see here, there is a differential settlement between the two slabs. There are three design considerations in the PCA method. First, flexural strength of concrete in terms of modulus of rupture, subgrade and subbase support in terms of modulus of subgrade, which we discussed in the last tutorial, which is obtained by the plate load test. Finally, traffic load, which does not depend on easels, so we will not change the axle loads to 18,000 pounds using the load equivalency factors. However, in the PCA method, we will treat each axle load and type, whether it's single axle or tandem axle, as it's by its own value. As you can see here in this image, this is the test for flexural strength of concrete. It is a 3-point bending test, where at the middle here you achieve the maximum stress, which relates to the modulus of rupture. Now let's talk about each item in more details. Flexural strength of concrete. The flexural strength of concrete is used in the PCA method in terms of the modulus of rupture obtained by third point bending and the ASTM designation C78 if you want to know more about this test. Here you have this concrete slab, as you can see, or a concrete beam where is subjected to loading P. This P is divided on two supports, P over 2 and P over 2. You will have this reaction here also P over 2, and this one will be also P over 2. If you draw a bending moment for this beam, it will look like this, where you have the maximum moment here, this value. So you can apply the equation of stresses due to bending. M over I multiplies Y. Here this C is Y, which is equal to D over 2, half the height of the cross section. Ix is B h cube over 12, or the height here is D, so B D cube over 12. You apply both C and I in this equation to obtain the modulus of rupture, MR, equal PL over BD square. Usually the modulus of rupture ranges between 8 to 10 root F-C, compressive strength of concrete, and it usually ranges between 600 and 700 pounds square inch. The modulus of subgrade will be equal to K subgrade if no subbase is used in the PCA method under the concrete slab, or the modulus of subgrade K will be equal to K composite, which represents both subbase and subgrade, and the subbase has two scenarios where it will be untreated subbase or treated subbase. You will assume the thickness of subbase, or it will be given in the equation. Here in this table we have the design K values for untreated and cement treated subbases. A untreated granular bases, you know here the subgrade modulus of rupture, and you assume the subbase thickness, let's assume 6 inches. So for example, you will get, if we assumed also the modulus of subgrade to be 100, you will get the K composite 140 for both subgrade and subbase. If it is cement treated subbases, it will have a higher modulus of rupture due to the treatment. So for example, at the same modulus of subgrade and at the same thickness, you will have K composite of 400 instead of 140. PCA traffic data. Usually the PCA traffic data method depends on average daily truck traffic, because passenger cars cause negligible damage to the concrete slab. As I said in the introduction that the PCA method does not use the ACELs for the design. There are load safety factors to account for impact behavior of the load of the traffic, and also acts as a safety factor. There are 3 cases for this load safety factor. For interstate highways and other multi-lane projects of high traffic flow and high volume, the load safety factor will be 1.2. For moderate volumes, load safety factor will be 1.1. For small volumes of traffic, the load safety factor will be 1. So at the end, it's very important to know that we need to have the exact number and weight of each axle type, single, tandem, and tridem if given. The concrete slab thickness is function of axle type, single or tandem, axle load, magnitude, number of repetitions, modulus of rupture, and modulus of subgrade and subbase. Our first design criteria, fatigue analysis. Fatigue analysis is based on the edge stress midway between the transverse joints. Fatigue analysis takes into consideration the flexural failure due to load repetitions. طيب نتيجة الفاينايت element models هم عملوا كذا موديل لإيه شكل اللودز أو الأكسلز اللي هتجيب الماكسيمم flexural ستريس على الكونكريت سلاب، ولقوا إن الشكل ده لما يكون التاندم أكسل لود موجود في الميد واي ما بين السلاب دي وبداية السلاب التانية، ده هيكون الكريتيكال لود لوكيشن بالنسبة للفتيج. Second design criteria erosion analysis, pumping, erosion of foundation and joint faulting. The most critical pavement deflection occurs at the slab corner when an axle load is placed at the joint near the corner. برضو في نفس الكلام في الإيروجن عملوا كذا موديل وعرفوا ان الكريتيكال لوكيشن اللي هيعمل الماكسيمم ديفليكشن اللي هيسبب لي ايروجن هو لما يكون اللود جاي على كورنر السلاب. يعني عندي كده دي هي السلاب وكده اللود يعتبر على الكورنر، عكس الفتيج اللود كان في النص. It's very important to know when you use concrete shoulder. The concrete shoulder reduces stresses and slab thickness. The erosion analysis is very important because we need to limit the loss of foundation under concrete surface, which might cause bumping of fine materials or joint failure between both slabs. PCA design tables and charts. Separate sets of tables and charts are used to evaluate fatigue and erosion damages. So the design depends on assuming a cross-section or thickness of concrete slab, and then check fatigue and erosion that would be developed in the pavement through its life. So we need to keep both types of these stresses, fatigue and erosion, within the allowable limits. As I said also in the introduction, the design in PCA method is an iterative process, which means that you assume a thickness of concrete slab in the beginning, usually between 9 and 10 inches, or obtain the thickness using the AASHTO method, and then check on the fatigue and erosion. زي ما قلت في بداية التوتوريال، الديزاين في طريقة البي سي اي ده iterative، مش بعمل ديزاين مرة واحدة وبقف زي الاشتو، لكن أنا هنا هفرض thickness للكونكريت سلاب في البداية تقريبا بيكون ما بين 9 و10 إنش، أو هجيب الثيكنس بطريقة توتوريال 7 اللي هي طريقة الاشتو، وهعمل تشيك على الفتيج والإيروجن. لو الفتيج والإيروجن اوف ليميتس هزود الكونكريت سلاب thickness ب 0.5، يعني سي مثلا أنا افترضت إن هو 9 وطلع unsafe fatigue أو erosion، هاجي الستيب اللي بعدها هاجي مزود الثيكنس اخليه 9.5 وهعمل تشيك تاني وهكذا لحد ما يطلع الفاتيج والايروجن جوه الليميتس. Now let's talk about the fatigue analysis. PCA tables define the stress in pavement slab for given conditions of. So the stresses that arise in the slab are function of slab thickness and modulus of subgrade or subbase. Two levels of stresses are defined for each axle type, whether it's single axle or tandem axle. You will obtain a stress ratio is equal to stress over concrete modulus of rupture. We will get the allowable number of repetitions from charts to use to reach failure. Divide the actual load repetitions which will be given or calculated by the allowable repetitions from the graph, multiplies 100 to get the fatigue damage as percent per axle type and weight. طيب بالنسبة للفاتيج analysis هخش في التيبل احسب الاسترس اللي موجود عندي. ده هيكون فانكشن في السلاب ثيكنس اللي انا افترضته في البداية، وفي المودولس بتاع السب جريد او السب بيز على حسب انا عندي سب بيز او لا. هيبقى عندي 2 ستريسز هجيبهم من التشارتس، واحد للسنجل اكسل وواحد للتاندم اكسل. هحسب بعد كده حاجة اسمها ستريس ريشيو، هقسم الاسترس اللي انا جبته من التيبل على الكونكريت مودولس اوف رابتشر اللي هيكون given. بعد كده هحسب ال allowable number of repetitions. بعد ما انا عرفت الستريس ريشيو هقدر احسب ال allowable number of repetitions اللي تسبب لي الفاتيج فيلير. هقسم بعد كده ال actual load repetitions دي اللي هتكون given او انت هتحسبها على ال allowable repetitions اللي انت جبتها من الشارت multiplies 100 عشان احسب الفاتيج percent لكل اكسل تايب. يعني هعمل الكلام ده كله للسنجل اكسل، ومرة تانية هعمله للتاندم اكسل، واجمعهم على بعض، ولازم السم يكون less than 100. دي كده design steps في الفاتيج analysis. Now let's talk about our first table. It is really important to know the title of this table: equivalent stress values for single axles and tandem axles without concrete shoulder. K of subgrade subbase pound per cubic inch single axle tandem axle. التيبل ده هيديني الستريسز للسنجل اكسلز والتاندم اكسلز لما ما يكونش عندي كونكريت شولدر في الطريق. عندي هنا برضو المودولس اوف سب جريد او سب بيز على حسب انا مستخدم سب بيز او لا، ورقم مكتوب سنجل اكسل بعد كده سلاش تاندم اكسل. يعني زي مثلا ال 825 دي سنجل اكسل بعد كده سلاش 679 ده تاندم اكسل. طبعا انت بتبقى فارض السلاب ثيكنس وليكن مثلا 10، بتخش وانت عارف المودولس اوف سب جريد سب بيز سواء كان كي كومبوزيت او كي سب جريد على طول مثلا 150، هيبقى انت عندك ستريس السنجل 186 والتاندم اكسل 173. طيب سي مثلا انت المودولس اوف سب جريد كان 130 زي ما هنشوف في الاكزامبل. طب 130 ده مش موجود في التيبل، ده موجود ما بين 100 و 150، فساعتها انت محتاج تجيب ستريس فاليوز عند ال 130 للسنجل وللتاندم. ساعتها هتستخدم linear interpolation ما بين ال 100 وال 150 عشان تقدر تحسب الستريس فاليوز بتاع 130. طب تعال نشوف كده example على linear interpolation. say مثلا احنا عندنا x1 y1 البوينتس الاولانيه 100 و 215. ال 100 ده المودولس اوف سب جريد، وال 215 هي الستريس بتاع السنجل اكسل 215. x2 y2 البوينت التانية اللي انا عارفها اللي هي 150 ده مودولس اوف سب جريد، والبوينت التانية السنجل 200. دلوقتي انا عايز اجيب الستريس بتاع 130 لما يكون سنجل اكسل. طيب الاكس والواي بتوع البوينت اللي انا عايز احسب عندهم، انا عارف الاكس اللي هو ال 130 ده المودولس اوف سب جريد، وعايز اجيب الواي ساعتها الستريس فاليو بتاع السنجل. قال لي والله الايكويشن بتاعت الواي y equal y1 minus y2 minus y1 over x2 minus x1 multiplies x minus x1. هعوض تعويض مباشر في الرول ده، هيحسب لي الستريس بتاع ال 130 عند 130 و 10 inches و 9.5 inches أنا آسف، هيكون 206 pound per inch square السنجل اكسل. نفس الكلام هعمله للتاندم اكسل، بس ساعتها الواي 1 والواي 2 هيتغيروا، هيبقى واحد ب 205 والتاني ب 183. التيبل ده زي اللي فات بالظبط، لكن وانا مستخدم كونكريت شولدر، فلازم تبقى عارف انت داخل في انهي تيبل. طب التيبل ده او الجراف ده بستخدمه عشان احسب ال allowable load repetitions. اقرا كده تحت fatigue analysis allowable load repetitions based on stress ratio factor with and without concrete shoulders. Fatigue analysis for each loading condition, axle type, single or tandem. Find the allowable number of repetitions from this chart. Allowable number of repetitions is function of stress ratio factor equal stress over strength. The stress I obtained previously in the last slide, the stress, and the strength is the modulus of rupture of concrete. الجراف ده هيديني ال allowable load repetitions. طب ايه اللي انا محتاج اعرفه عشان احسب ال allowable load repetitions؟ اول حاجه بص كده، الاكسس ده مكتوب هنا single axle loads كيلو باوند، ومكتوب على اليمين tandem axle load كيلو باوند. يعني الارقام دي واحد للسنجل على الشمال واللي على اليمين للتاندم اكسل. دي اول حاجه. الارقام دي وانا بخش في الجراف بضرب في اللود سيفتي فاكتور. يعني سي مثلا هو اداني ان السنجل اكسل ويت 30 كيلو باوند، انا مش هخش هنا في الشارت ده ب 30، هضرب في الفاكتور وليكن مثلا 1.2. هو قال ده هاي ترافيك فوليوم، فانا هخش مش هخش ب 30، هخش ب 30 ملتبلايز 1.2. طيب هوصل بايه؟ هوصل بالستريس ريشيو فاكتور. الستريس ريشيو فاكتور ده ايكوال ايه؟ ايكوال الستريس اللي انا جبته من التيبل بتاع السلايد اللي فاتت مقسوم على المودلز اوف رابتشر اوف كونكريت. هبقى جبت هنا مثلا بوينت وهنا معايا بوينت، هوصل ما بينهم هيديني هنا ال allowable load repetitions. For each loading condition axle load, calculate the damage for each axle load. يبقى الستبس اللي انا عملتها قبل كده دي هكررها لكل axle load. هحسب الدامج percent او الفاتيج percent equal actual number of load repetitions على ال allowable load repetitions مضروب في 100. بعد كده هجمع كل الدامج percentages اللي انا حسبتها لكل اللودز سواء كانت single axles او tandem axles، لازم يكون السم less than 100. ده ساعتها هيكون design safe for fatigue. لو رقم طلع اكتر من 100 هزود السلاب thickness ب 0.5 انش وارجع اعمل نفس الحل تاني لحد ما يكون less than 100. Now let's talk about erosion analysis. PCA tables define the erosion factor in pavement slab for given conditions of. So the erosion factor is function of slab thickness and modulus of subgrade or subbase. Two values for erosion factor are defined for each pavement structure. So there is an erosion factor for the single axle and another one for the tandem axle. Get the allowable number of repetitions from chart also. It is similar to fatigue analysis. Divide the actual load repetitions given or calculated by the allowable repetitions calculated only multiplies 100 to get the erosion damage per axle type and weight. طيب زي ما عملنا في الفاتيج اناليسيس، انا كنت بحسب حاجه هناك اسمها ستريس ريشيو فاكتور، لكن هنا انا عندي erosion فاكتور ده بجيبه من التيبلز. ده بيكون فانكشن في السلاب thickness والمودولس اوف سب جريد او سب بيز، وعلى حسب انا عندي كونكريت شولدر ولا لا، وبرضه على حسب التايب اوف لود ترانسفير سواء كان using دول بارز او الاجريجيت انترلوكينج. في تشارتس مختلفة لكل الكيسز دي. هجيب erosion factor للسنجل اكسل وللتاندم اكسل لكل ويت اكسل لوحده. بعد كده هحسب ال allowable number of repetitions من التشارت. هقسم ال actual load repetitions سواء هتكون given او انت هتحسبها على allowable repetitions مضروب في 100. بعد كده هكون جبت ال erosion damage او percent لكل اكسل ولكل ويت، هجمعهم ولازم السم يكون less than 100. لو طلع اكتر من 100 هزود الثيكنس بتاع السلاب half inch وارجع اعمل نفس البروسيس تاني لحد ما يبقى السم less than 100. Our first table in the erosion analysis. It is very important to read the title of this table: Erosion Factors for Single Axles and Tandem Axles, Doweled Joints Without Concrete Shoulder. So the type of load transfer here is dowel bars without concrete shoulder, and we are given also the slab thickness that we are going to assume and the modulus of subgrade subbase for single axles and tandem axles in the same table. The next table, erosion factors for single axles and tandem axles. However, the load transfer type here is aggregate interlocking without concrete shoulder also. Here we have doweled joints and concrete shoulder. Finally, we have aggregate interlocking with concrete shoulder. So here we use this graph to obtain the allowable load repetitions. We know the single axle loads in kilopound and the tandem axle loads. It is similar to what we did in the fatigue analysis. This graph here is for erosion factors without concrete shoulders. You know already the axle loads, and also the erosion factor is obtained from the table in the previous slides, so you can get the allowable load repetitions. This graph is similar to the previous one, but here erosion factors with concrete shoulder. For the erosion analysis, for each loading condition or axle load, calculate the damage for each axle load. The damage percent is equal to actual number of load repetitions over the allowable number of load repetitions multiplied 100. And as I said, the damage or the summation of damage should be less than 100. This slide here shows a summary for the PCA design method. First, you assume the concrete slab thickness. You will be given the subgrade properties like K subgrade or subbase, and also you will assume or given the thickness of subbase. Let's talk about the fatigue analysis. So we have a stress for single axles and another stress for tandem axles. You get them from tables. You will divide this stress by the concrete modulus of rupture to obtain the stress ratio for single axles and another stress ratio for tandem axles. You will enter another graph, and by knowing the stress ratio and the axle load multiplied by the load safety factor, you will get the allowable number of load repetitions. The fatigue percent is equal to the actual number of load repetitions by the allowable number of load repetitions multiplied 100. That is how you apply the fatigue analysis design steps. For the erosion analysis, you will get directly from the table the erosion factor for single axles and erosion factor for tandem axles. Also, by knowing the axle load multiplied by load safety factor, you will get the allowable load repetitions for erosion analysis. And similarly to what we did in the fatigue analysis, you will divide the actual load repetitions by the allowable load repetitions multiplies 100 to get the erosion percent, and you have to check that the summation of each is less than 100 for each analysis type. Let's take an example. Design rigid pavement. We are given the key composite is 130. The thickness of subbase is 4 inches and it is untreated subbase. Concrete modulus of rupture is 650 psi. Load safety factor is 1.2 for high traffic volume. We are also given that this concrete is doweled. The load transfer type is doweled bars and no concrete shoulder is used. And we are given this traffic study, axle weight, single axle, load in kilopound, and the expected repetitions, or you can name this column as the actual repetitions. We are also given the weights of tandem axle loads and their actual or expected repetitions. So now let's assume that the thickness of concrete slab is 9.5 inch, and let's check the fatigue and erosion for this slab thickness. First, for single axle load, we will get the equivalent stress by linear interpolation from the table as we did. You will obtain the stress factor for single axle is 206 divided by the modulus of rupture. The stress ratio will be 0.317, and the erosion factor from the table will be 2.59. Now, the single axles that we are given in this column will be multiplied by 1.2, the factor of impact and the safety factor. So the 30 multiplies 1.2 is 36, 28 multiplies 1.2 is 33.6, and so on. We are also given the expected repetitions. Now we need to obtain the allowable repetitions using the graph. Now we know the axle load multiplies load safety factor and add the stress ratio of 0.37, so I can calculate the allowable repetitions for each axle type and load. For the first axle, which weighs 36 kilopound, the allowable number of repetitions is 27,000. 33.6 is 77,000. 31.2 is 230,000. 28.8 is 1.2 million, and the other axle loads are unlimited. So unlimited means that regardless the number of repetitions of this axle load, it will not cause fatigue failure in the concrete slab. Then you obtain the fatigue percent. You divide 3 by 4, column 3 divided by column 4, so 6,310 divided by 27,000 will give you 23.4, and so on. Now let's do the erosion analysis. Our aim at the end is to obtain the allowable repetitions in order to obtain the damage percent. The allowable repetitions are obtained using the erosion factor and the axial load multiplies load safety factor. You will get the allowable repetitions. Damage percent for erosion is equal to column 3 divided by column 6, expected repetitions divided by allowable repetitions for erosion. Now let's see how to obtain the allowable load repetitions for fatigue analysis. I will do only single axles and tandem axles will be the same. Remember that we enter single axles or tandem axles by multiplying the axle load with load safety factor. So the first axle weight is 36 and we have the stress ratio factor 0.317. So you will join 36 with 0.317. You will obtain here this value as the allowable load repetitions. Then the other value is 33.6. Here you will join 33.6 with 0.317. You will obtain 77,000 repetitions, and so on for the 31, 28.8, 26.4, 24, 21.6, and 20 and 19.2. It is really important to know that at 26.4 your arrow will go off table, which means that it's unlimited. So starting 26.4 till reaching 19.2, all those axle weights can repeat infinite numbers around the concrete slab and the fatigue failure will not happen. Now the solution for tandem axles, we have to obtain a new stress number from the table, and the stress ratio factor will change also. It will be 0.295 instead of 0.317 as the case was in the single axle. You will obtain also the erosion factor from the table of erosion analysis. These are the axle loads. They will be multiplied by the load safety factor, which is 1.2. You will obtain the axle loads multiplies load safety factor, and then you will obtain directly the expected, the allowable repetitions, because the expected are given. Then you will calculate the fatigue percent. It is equal to expected repetitions divided by allowable repetitions, and the same we did for erosion analysis. Now the total fatigue damage is 62.8% and the total erosion damage is 38.9%. The fatigue is less than 100 and also the erosion is less than 100, so it is safe to design for 9.5 inches. However, if you try to decrease the concrete slab thickness to be economic, if you try to repeat the example at 9 inches, it will result in fatigue damage of 142%, so it will be unsafe. So the minimum thickness for this concrete under this traffic load will be 9.5 inches. Now let's see another example. We have 8-lane highway, 4 lanes per direction. The annual average daily traffic is 1000, total traffic in both directions. given that the truck percentage is 15% of the traffic and the other traffic is passenger cars, which can be ignored in the structural analysis. The design period is 20 years and the annual growth rate is 2%. The design truck has 2 single axles and 1 tandem axles, weighs 6,000 pounds, 20,000 pounds, 38,000 pounds respectively. We need to check the suitability of using 6.5-inch concrete slab. By PCA method, we are given the modulus of subgrade reaction is 100 pound cubic inch, concrete modulus of rupture is 650 pound square inch, and assume a load safety factor of 1, so it is a small volume road. Assume that the pavement has leveled joints and concrete shoulders. So now let's obtain the expected number of repetitions, because it was not given. The directional distribution factor multiplies the lane factor are equal to 0.4 or 40%. How did we know this number? Here you can read the title: percentage of total truck traffic on design lane, the number of traffic lanes, 2 directions, and here the percentage of truck in the design lane. We have 6 or more, we have 8 lanes in this highway, so the design lane factor will be directly 0.4. So the directional distribution factor multiplies the lane factor here are both 40%. The growth rate to obtain the traffic in the future is equal to 1 plus j power number of years minus 1 over the growth factor or growth percent. It will be 24.3. So the number of trucks in the design lane, or the actual number of repetitions, is equal to 1000. The total number of vehicles multiplies 15% or 0.15 to obtain the truck share of traffic only, multiplies 365 to get them per year, multiplies 24.3 to get them at the future design year, multiplies 0.4 to get the volume on, or I mean the number of repetitions on the critical lane. It will be 532,000. So again we will do both erosion analysis and fatigue analysis. For single axle, the stress will be 294 psi, so the stress ratio will be 294 divided by modulus of rupture, it will be 0.4. The erosion factor for single axle will be 2.65. For tandem axle, the stress will be 251, the stress ratio will be 0.39, and the erosion factor will be 2.7. So here we have 6,000 pound single and 20,000 pound single and 38,000 tandem. The load multiplies load safety factor, which was 1, so the numbers will remain the same. The expected repetitions, we calculated them, and the allowable repetitions are unlimited for all axle weights, so the fatigue percent is 0. However, for the erosion, the single axles are unlimited and the tandem axle produces a damage percent of 17. So total damage fatigue is 0. So this concrete slab will not fail under fatigue by any mean. The total erosion damage is 17%, which is less than 100, so we are safe. So 6.5 inches is safe design, and we need to check on 6 inches to be economic in our design. I also left you 2 papers on how to apply the PCA design method. Here you have the trial thickness, sub-base, sub-grade, modulus of rupture, load safety factor, type of load transfer, concrete shoulder used or not, design period, axle load multiplies load safety factor, and so on. So this is the same paper but for tandem axles. The previous one was for single axle. Thank you very much. Please do not hesitate to contact me on my email if you have any questions.